Naive fixed-size chunking guarantees context loss in structured PDF documents. When a 1024 token window splits a paragraph from its preceding section header, retrieval precision drops below 40%. The immediate solution involves defining a hierarchy of separators. Start with the most significant delimiter, typically 2 consecutive new lines, followed by single new lines, then periods, and finally commas. This ordered array ensures the splitter prioritizes structural breaks over arbitrary token limits, preserving logical units before resorting to smaller splits. This method prevents critical context fragmentation, which is the primary cause of hallucination in RAG systems built on technical documentation. Implementing the Recursive Character Text Splitter requires careful tuning of the separator's parameter. For technical manuals, the optimal sequence is often \n\n, period, space, space, and finally the empty string. The chunk size parameter, for example 512 tokens, acts as the maximum limit only after all structural separators have been exhausted. Crucially, the chunk overlap must be set to include the preceding structural element, such as the section title, ensuring continuity. A 10% overlap is standard, but for highly technical documents, increase this to 15% to capture cross-reference context without introducing excessive redundancy into the vector store. Standard text extraction fails on multi-column layouts, tables, and embedded figures. To maintain spatial context, we must integrate layout-aware parsers. Libraries like Unstructured or Layout Parser identify bounding boxes for text blocks, tables, and images. This process converts the PDF into a sequence of structured elements, not just raw text. Each element is then treated as a potential chunk boundary, preventing a table row from being arbitrarily split from its column headers. This structured approach ensures that the semantic meaning derived from visual proximity is preserved during the chunking phase.
Tables present a unique chunking challenge. Instead of embedding the raw table text, which often exceeds token limits and confuses the language model, extract the table structure separately. Convert the table into a concise markdown format, or, preferably, generate a summary of the table content using a small, specialized language model. Store this summary as the primary chunk text and the full markdown table as metadata. This dual approach allows fast retrieval via the summary while providing the full context upon generation, preventing the embedding space from being polluted by dense, unstructured data. Contextual metadata is the retrieval key. Every chunk derived from a PDF must inherit critical attributes: the document title, the page number range, and the immediate section header. Use a custom text splitter that automatically prepends or appends the current section header to the chunk text before embedding. This ensures that even if the query does not explicitly mention the section, the embedding space captures the necessary context, significantly boosting the mean reciprocal rank score during evaluation. This technique is non-negotiable for documents with deep hierarchical structures. Semantic chunking groups sentences based on embedding similarity, moving beyond fixed token counts. Calculate the cosine similarity between adjacent sentences. A drop below a predefined threshold, typically 0.85, signals a topic shift and defines a chunk boundary. This method dynamically adjusts chunk size based on content density. However, this approach is computationally expensive. Pre-calculate and cache the embeddings for static document sets to mitigate latency during the ingestion pipeline. Use a fast, small embedding model like all-mini LLM-L6-V2 for the similarity calculation step to maintain acceptable throughput.
Fixed chunk sizes are inefficient when dealing with diverse query types. Implement dynamic chunk sizing based on the expected query complexity. For high-level summary queries, use larger chunks, perhaps 1024 tokens, to capture broad context. For specific fact retrieval, use smaller, targeted chunks of 256 tokens. This requires maintaining multiple vector stores indexed with different chunking strategies, selecting the appropriate index based on a pre-query classification step. Classify the incoming query using a zero-shot classifier to determine if it requires broad context or specific detail retrieval. To implement metadata propagation effectively, subclass the base text splitter class provided by your framework, such as LangChain or Llama Index. Override the split text method to iterate through the document structure provided by the layout parser. Before yielding a chunk, access the parent node information. Inject the parent node title into the chunk dictionary under a key like source section. Ensure the embedding model is trained or fine-tuned to recognize and utilize this injected metadata during vectorization, treating the metadata as part of the content to be embedded. Chunking effectiveness is measured by retrieval quality, not just token count. Use Mean Reciprocal Rank, or MRR, to evaluate how highly ranked the correct chunk is for a given query. A high MRR indicates successful chunking. Alternatively, use Recall at K, ensuring the relevant chunk appears within the top 5 retrieved results. If Recall at 5 is below 90%, the chunking strategy is failing to preserve necessary context boundaries. Establish a small representative golden dataset of query answer pairs to run these metrics automatically after every pipeline change. Even with optimal chunking, noise exists. Implement a post-processing re-ranking step using a cross-encoder model. The cross-encoder takes the query and the top retrieved chunks, scoring their relevance more accurately than the initial vector similarity. This step filters out contextually weak chunks that passed the initial retrieval threshold due to embedding proximity, ensuring only the most precise information is passed to the final language model generation stage. Use models like BGE Re-Ranker for this final precision boost.